this video we're going to talk about different types of graphs that we might come across during science class this year. But before we can do graphs, the first thing we have to be able to do is interpret data tables. So hopefully we've all seen at least some sort of data table before, something like this. Basically all data tables are is a way for us to organize our data to present it in a way that other people can read and make sense of, right? If you take a whole bunch of random numbers down on the page, somebody might not know how to interpret that, but the key with data tables is we organize our information in nice columns with titles and headings, and then whoever we want to share our data with can then look at it and kind of know what's going on. So the key with the data tables is to use these titles to help us sort out the information. So in this data table here, the two columns we have are the pH of the water and the number of tadpoles. So you guys don't need to know what pH means. It basically tells us how acidic something is. So an acid would have a really low pH. So the pH of the water just tells us how acidic it is. But for this example, we know that everything in this column here has to do with the pH of each of these different samples, and everything in this column here has to do with the number of tadpoles that are living in the water when it's at that given pH. So the titles really help us make sense of what's going on, and then this data table even has a title for the whole thing that tells us basically we're looking at the pH of water and how that affects the tadpoles' growth in this water ecosystem that they're living in. All right. So the other thing with the data tables is that usually you're going to see the independent variable first in the data table. If it's a well-constructed data table, you'll see the independent variable first, and then the dependent variable or multiple variables will be listed afterwards. All right. So these are the parts of the data table we want to know. We have the independent variable here in this column and the dependent variable here in this column. All right. So just looking at each line individually, we know that when the pH was 8.0, the number of tadpoles there was 45. When the pH was 7.5, the number of tadpoles was 69. So we can look at it almost like data points here, exactly like data points here in our data table. All right. So we can also have some more complex data tables, right? This first example was pretty simple, right? We had one independent variable and one dependent variable. But we can also have data tables that have more than one dependent variable. So in this case, the independent variable here is who the person is. So the name, this would be the independent variable technically in this example. It's not so numerically oriented as the first one, but the dependent variables here would be age, height, and weight. Right? So we could look at this data table and say, okay, if we are looking at Fred's information, that's this whole column here. Right? And if we're looking at, let's say, Daphne's information, right, that's this whole column here, or sorry, row. And then if we want to know the weight for Fred, right, we would go to the weight column over here and look at Fred, and we just kind of go over here to Fred and the weight, and his weight would be 800, right? If we wanted the height for Shaggy, right, we could go to the height column and go to Shaggy and see where they meet up here. Right, so Shaggy's height would be shown as 1.7. This is in meters, right? So he's not 1.7 feet tall, but right. So we can just look and see, go across the columns and see where these data points match up. Alright, so when we go to do graphs, the first type of graph, and perhaps the most common type of graph you'll see in science, is a scatter plot. So what a scatter plot is going to look like, and I'll skip forward here just for a quick sec. A scatter plot is basically going to look something like this. All of these 6 examples here are scatter plots. We're basically just putting our points down as dots on an XY axis system. Alright, so if we look at some of the characteristics of scatter plots, first of all, they help determine the relationship between two variables, and we'll talk about relationships in a few minutes. So we're using the XY plane here, right? So we could see a scatter plot that has an XY plane like this. Hopefully we've all seen an axis system like this in math class, right? So we could have an axis system that looks like this, but if you notice on the graphs we just showed, we only showed the positive x and y axis. right? So if you see this, it's really just this section of a complete coordinate plane. So if you see something like this, it's fine, it's still a good graph, it's just we're only looking at the positive numbers. Okay, so the important thing here, the independent variable must always go on the x-axis, right? So in this graph example here, we would put the independent variable here. So the easiest way to remember this is the phrase, the ivy grows on the ground, which may or may not be true in real life, but the ivy grows on the ground, so the IV, the independent variable, grows on the ground, the x-axis. Alright, so you're going to see the independent variable on the x-axis, and then we're going to put the dependent variable on the y-axis. Alright, so you make sure all the time that you keep your independent variable on the x-axis, because that's how you properly represent that information in a graph. Okay, so looking at some of these types of relationships like we talked about, there's two main types of relationships that we're going to be looking at. I guess three, but a positive relationship. That means that as the independent variable goes up, the dependent variable goes up as well. So if we look at a positive relationship, we would see as the independent variable goes up, as we go to the right here along the x-axis, as the independent variable goes up, the dependent variable goes up as well. So we would see some type of relationship that's trending upwards like this. Alright, for a negative relationship, what we'll see is as the independent variable goes up, the dependent variable actually goes down. So they both don't go up at the same time, like in a positive relationship here. In a negative relationship, as we go up in the independent variable, the dependent variable decreases. So we'll end up with a relationship that looks something like this. It's not necessarily going to be a straight line all the time, right? If we had a positive relationship, for example, it could look maybe like a curve like this. Anything that trends upwards is going to be a positive relationship. Anything that trends downwards is going to be a negative relationship, right? The stronger the relationship is, we are going to see that the data points really kind of close together and form a kind of distinct, obvious shape. Alright, so if we look at these examples here, we can try and identify what type of relationship there is in each of these. Alright, so I want to start with example B here. If we look at this, if you want to maybe pause the video right now and think of what type of relationship you think this would be. But if we look at this, we see the trend of these dots is going upwards as we go from left to right. Okay, so this is going to be a positive relationship because as the independent variable increased, the dependent variable also increased. Alright, so again, because it's trending upward, that would be a positive relationship. For example C here, I'll do this in a different color here. For example C, right, we can see a downward trend in this relationship. So as the independent variable went up, the dependent variable actually went down. Right, so from left to right, we can see it's going downwards. That means this is going to be a negative relationship. So now I want to look at example A here. If we look at example A, maybe pause the video and see what type of relationship do you think this would be. Alright, so if we look at this, we can't really make out any trend in this data, right? We can't necessarily say that it goes this way, or maybe it could go this way. We don't really know. There's no obvious pattern. Here we have a pretty obvious trend, positive and negative, for examples B and C. But for A, we can't really make any sense of this data, right? We can't definitely say that it's going upwards or downwards. So this would actually be called no relationship, we could say for this. So you're going to see no relationship if the data is all just kind of scattered about. It might look like a blob. You can't really tell what's going on. This would be called no relationship. If we look at example D down here, we can see this one actually has a kind of flat line going across. So this would be called a constant relationship. So this, because it's staying constant, it's not increasing or decreasing, it's staying the same, right? That's what constant means. So this would be called a constant relationship because the data points are neither increasing nor decreasing as we increase the independent variable. Alright, those are the only ones we're going to focus on here. There are a couple of other examples here, but these are the main types of relationships you need to know. definitely know positive and negative relationships, but it's also helpful to know if something has no relationship or maybe a constant relationship as well. Okay, so the last thing about scatter plots here is the concept of a best fit line. So a best fit line, it basically just summarizes the data. It represents the gist. It shows us kind of just what is the overall trend in the data. So a best fit line does not connect all the dots. This is very important. This that I'm drawing right now is not a best fit line. No, not a best fit line. Okay, the best fit line is the example that's already on the page here. It's always going to be a straight line like this if we're talking about a linear relationship or a relationship that reflects a line. It's always going to be a straight line. So what you want to do when you're constructing a best fit line is just kind of look at your data and draw a line that kind of cuts through the middle of all the points and accurately reflects the slope of these data points. Right? So if we look at these data points here, right, they have this trend that goes kind of like this, right? What we don't want to do is draw a best fit line something like this, right? Because this doesn't accurately reflect the slope of this line, right? We have the data points that kind of are trending this way, right? So we want to make sure that the slope of our line is accurately representing that set of data, right? So if we drew a slope like this one, it wouldn't really accurately reflect the data, just like you wouldn't want to draw a line like this. This line obviously doesn't fit with these data points. So we want to draw a line that really reflects accurately the slope of the data points, right? So we have this line that goes, kind of cuts through the middle. There's a lot of, there's about an equal number of data points below and above the line. That's a good sign that you're cutting through the middle. And we have a slope that kind of hugs these data points as we go upwards, right? So line graphs are the next type of graph. These are going to be a little different than scatter plots because with line graphs, you do actually connect the dots. So we have all of our data points here with line graphs, and with a line graph, you're actually just going to connect each dot to each other. So that's the difference between a scatter plot, where we might draw a best fit line, or maybe we don't draw any line at all and just leave the data points, and a line graph where we're always going to connect our data points to one another. Alright, so some characteristics of line graphs. The reason we use line graphs most of the time is to show changes over time, right? So if you were trying to maybe track how much running you did over a given week, you could represent that with a line graph, because in the span of that week, we're talking about what amount of running you did over time. So on Monday, you did this much. On Tuesday, you did this much. We could show that with a line graph because that's something that's happening over time, right? They can also allow us to make predictions. So if we look at this line graph on the next page here, we can kind of make predictions of what might happen if we were to extend this graph out further to the right. Alright, so if we look at this, we can see, okay, there seems to be an upward trend here. We have this little glitch in here between Wednesday and Thursday that maybe we can't explain. So really, we would need some more data, but we could possibly predict here that this line might keep going up this way, and then maybe at some point it would go down again and come back up because we do have this little anomaly or glitch in the data here, right? But when you look at a line graph, you can often tell what direction the trend seems to be going. So a better example might be if we look at a graph that looks something like this, and we wanted to see, well, what would the graph be doing as we keep going out this way? Well, we could say, okay, it is kind of just increasing up and down slowly over time, so we could say maybe it would look something like this. Alright, so with line graphs, you can predict beyond the data sometimes, and that's actually called extrapolation, if anybody has heard of that term before. Okay, the next type of graph, bar graphs. So what we have to do with bar graphs is show differences between different groups. So these are going to be slightly different than line graphs because we're not looking over time, although you can do that with a bar graph. It's really better suited for a line graph. The thing we're doing with bar graphs is comparing different groups. So this graph here was showing how many customers each of these employees served every week, right? So we could compare how many customers Bob served to how many customers Alice served, right? And the bars make it very easy, right? We're just getting a customer count here on the y-axis. the bars make it very easy to compare between these different groups. And over on the right here we have after school activities, right? So how many students liked each of these after school activities, right? So we can compare how many students like to play sports compared to how many students like to watch TV at home, right? So we can easily compare between groups with a bar graph. Okay, the next type of graph, pie graphs. What these are doing is they're showing parts out of a whole. That's very important. Pie graphs are always representing some sort of whole, and we're looking at how much each group takes up out of that whole. So here, this graph is basically what gases make up the air that we breathe. Right, so the air we breathe is actually mostly made of nitrogen, and we can tell by the graph that nitrogen has the most because A, it's labeled here as 79%, and B, we can look at the graph and see that this nitrogen, being the blue color here, we can tell by this key over here that nitrogen is blue, we can tell that takes up most of this pie, right? The nitrogen is taking up 79%, but also most of the area of this circle, okay? So usually if it's a good pie graph, we'll hopefully get labels for the percentages, right? So we have labels for the percentages here that give us a really accurate and precise definition of how much each part takes up out of the whole. So these parts are usually going to be shown as a percentage. You may see a pie graph with fractions every now and then, but really percentages are better. And again, like we talked about, the bigger the pie piece, the bigger the part of the whole it takes up. So we know because nitrogen has this big pie piece here, it's taking up a lot of the whole. Whereas oxygen, right, takes up a smaller part of the whole here. So we know there's less oxygen in our air than there is nitrogen. Okay, and with pie graphs, we can also determine if we have the number of people in each group. We can determine, if we want to find the number of people in each group, we can find that if we have the percentage and the total. So what we could do here is say, let's say we had 100 people in our group. So if we know that the total number of people in the study that we're looking at is 100, then we can look at this pie graph and say, well, how many people total actually like maybe pumpkin pie, let's say, right? So if we know that pumpkin pie is 30% of the people, and we have 100 people, then we would end up with 30 people liking pumpkin pie, right? This is a real easy example because percentages are out of 100, but right, so we know that even though pumpkin is 30% here, it actually equates to 30 people as well, because out of 100 people, 30 people would give us 30%. If we look at a second example here, let's maybe try something a little more difficult. If we have 200 people. So how could we figure out if we have 200 people and we know that, let's say, 30% of them like pumpkin pie, we can use the pumpkin pie example again, right? So if we have 30% of them liking pumpkin pie, how could we figure out how many people total would like pumpkin pie out of this 200, right? So the easiest way to do this would just be to take 30% of 200. So we can multiply 200 by 30%, or as a decimal, this would be 200 times 0.3, and this would give us 60 people. So if we know the percentage and the total, then we can figure out the number of people in each group based on our pie graph. Alright, and the last thing, we're going to touch real briefly on creating a graph. I'll do another video on actually graphing data, but when we're looking at graphs, we need certain parts to be included in every graph that we create. Right? So when we're doing this, you need a title on your graph, right? So the title of this graph is perceived human hearing. Right? So how much we can hear at each different pitch or frequency level. Right? So the title of the graph tells us what we're actually looking at. You also need axis labels. Okay, so axis labels tell us what is represented on each of the axes, right? The x-axis in this case is frequency, and the y-axis is sound pressure level, or basically the intensity of the sound, right? So the axis labels are very important as well. You also need scales for your axes, right? So the scales here, right, I kind of block this one off, but you can see, right, how each of the numbers is going up for each tick mark, right? And for this one, we're going up by tens for each tick mark, right? so we can see what scale we have on the axis. You need to include numbers on your axis scale, or else your data is meaningless. No one's going to know what your data actually means if you don't have numbers that kind of give you a benchmark. And you also need, the last part is to just graph your data, right? So here they made a line graph and graph their data that way. Alright, so you need, for each graph that you make, a title, you need axis labels, you need axis scales, and you need to actually graph the data itself. Alright, thanks for watching this video on graphing, and I'll see you in the next one.